The divergence theorem. The divergence theorem, proven by Carl Friedrich Gauss, here is a theorem that relates a triple integral to a second integral. The second integral is the flux integral. How is it possible then that we can compare and relate the flux integral to the so-called divergence? Well, I think it would be helpful to understand the idea of the divergence. So let's first take a solid here with a surface S sub 1 and S sub 2. S sub 1 is said to be oriented by an upward unit normal vector, and S sub 2 is here the surface is oriented by a downward unit normal vector. We want to be able to calculate the so-called divergence. That is the amount of fluid flow across a surface with respect to a particular point, the measurement of that fluid flow as the fluid crosses a certain interval. In the measurement of that, we are able to classify and discuss the idea of divergence. How much amount of the fluid diverges away from a particular point. It could be a source point, or it could be a sink, or it could be incomprehensible. What does that mean? Well, look here, the source point here in the middle, if the divergence of F is positive, then we say that the point there is a source and that the fluid flows here away or out of the source. If the divergence is negative, that means that the fluid, or maybe even not fluid, but some kind of electromagnetic force field, if you will, could also be the source. So if the divergence is negative, we have a sink where the so-called vector field flow is toward the particular point. If the divergence is F, then here we neither have a sink nor a source point. The fluid flows evenly across. So notice that this double integral is the flux itself. So we can calculate the fluid flow by using a triple integral. Carl Friedrich Gauss helps us with this. So let's look at some problems and see if we can make some sense out of it. The neat thing about this is that for the divergence theorem, you're only computing the divergence of F with respect to a triple integral over the solid here in terms of the change in the volume. If the instructions say evaluate the divergence both ways, one evaluating the flux and then secondly evaluating the triple integral, just do it one way. Just evaluate this solution based on the triple integral and you're done. And that's what I have done, and that's what I employ also to you. So the first thing we need would be the divergence of F. So this is 2x. Remember, the divergence is a scalar, plus 2y plus 2z. And you see the regions for here for x, y, and z. And so we have the triple integral. They all go from 0 to a. The divergence is 2x plus 2y plus 2z. And here we can use dz, dy, dx. First, integrate with respect to z. If you want, you can pull that 2 out in the front. That's fine either way. So here we have 2xz plus 2yz plus 2z squared divided by 2, which is just z squared. Here z is evaluated from 0 to a. So we replace the z with a. So we have 2ax plus 2ay plus a squared dy dx. Integrate now with respect to y. So we have 2ax y plus 2ay squared divided by 2, which is a y squared plus a squared y. And y is evaluated from 0 to a. This is dx. Have the integral from 0 to a. Replace the y with a. So this is 2a squared x plus a times a squared. So this is a cubed plus a squared a, which is a cubed. So this is just write it there, I guess. A cubed plus a cubed, or just 2a cubed, right? So let's write that. This is 2a squared x plus 2a cubed. This is dx. So here we have 2a squared x squared divided by 2 plus 2a cubed x. X is evaluated from 0 to a. So this gives us a squared x squared, which is, just write it, plus 2a cubed times a. So we get a to the fourth. Here we get 2a to the fourth. So this gives us 3a to the fourth. And that's a very neat volume formula. What about this one? Notice that the divergence of f comes out to be 1 plus 1 plus 1. The divergence is the partial derivative of the first term with respect to x, which is 1. The partial derivative of m with respect to y is 1. Then the partial of here, p with respect to z is equal to 1. M. Used to seeing it like that for conservative vector fields, plus the partial of n with respect to y plus the partial of p with respect to z. Forgive me, I didn't state this earlier. Well, if that is the case, then we can calculate this triple integral over the solid. This is 3 times dv. This is 3 times this triple integral over the solid of dv. This is a sphere, and so the volume for a sphere is 4/3 pi r cubed, and r is equal to 3. We can go through the work with this, but I think this is very straightforward, very static. So this is equal to 3 times the volume. Here the volume is with respect, the radius with respect to 3. So this gives us 4 pi times 3 to the third. So we get 27 times 4, 108 pi. What about this divergence? So this is 1 plus 2y minus 1. That's equal to 2y. Notice that the region, or really the solid, so based on x squared plus y squared equal to 25, we have 0 less than or equal to r less than or equal to 5. And then it's a complete circle, so 0 less than or equal to theta less than or equal to 2 pi. Then z goes from 0 to 7. So we have this triple integral. And the divergence there is 2y, so this is over the solid, 2y times with respect to the change in the volume. So this 2y is converted to cylindrical coordinates. This is 2r sine theta. I'm going to convert that to the cylindrical coordinates, so we have that r factor. I'm going to use d theta, dr, dz. So theta goes from 0 to 2 pi, r goes from 0 to 5, and then z goes from 0 to 7. Now, why am I evaluating with respect to theta first? Because this is a sine theta and is by itself, and here this integral is going from 0 to 2 pi. So when I integrate sine, I get cosine. I evaluate cosine at 2 pi, I get 1. I evaluate cosine at 0. It's a complete unit. It's closed. And so if it's closed here, then the energy that's exerted is 0 with respect to the fluid flow. So if you see that, then you're mostly done. This is 2r to the second sine theta d theta dr dz. Integrate with respect to theta. So this is 2r squared cosine theta. And integrating that sine, we get negative cosine theta. Cosine theta is evaluated from 0 to 2 pi dr dz. So this is negative 2, the integral from 0 to 7, the integral from 0 to 5. So r squared, cosine at 2 pi is 0, minus cosine at 0 is 0, dr dz. We get 0. Nothing from nothing leaves. You got it. Nothing. Say it again. Say it loud. Okay. Let's look at this one. This will be the last one. So the divergence of f is equal to, take the derivative here with respect to x, we get e to the z. The derivative here with respect to y is e to the z. And the derivative here with respect to z is e to the z. So this is 3 e to the z. X goes from 0 to 6. Y goes from 0 to what? Well, if we let z equal 0, then y here would be equal to 4. So y goes from 0 to 4. And then z goes from 0 to 4 minus y. Right? So letting z equal to 0, this implies that z equal to 4 minus y is 0 equal to 4 minus y. So y is equal to 4. So we have this triple integral. We better calculate z first. So the divergence is 3 e to the z. Need to write this dz. Doesn't matter about the rest. So dy dx in terms of the order does matter, but the order there doesn't matter. It's important to have, if the upper or lower limit is a variable, to get those out the way first. Don't leave variable limits of integration for the last integral. If so, you get a function and not a number. So y goes from 0 to 4, and x goes from 0 to 6. So integrate first with respect to z. 3 goes out in the front. It's the integral from 0 to 6, integral from 0 to 4. The integral of e to the z, dz, is e to the z. Z is evaluated from 0 to 4 minus y. Then here we have dy dx. So this is 3 times the integral from 0 to 6, the integral from 0 to 4. We evaluate here the upper limit, z at 4 minus y, so this is e to the 4 minus y. Then this is minus e to the 0, dy dx. We can clean that up a little bit. So this is 3 times the integral from 0 to 6, the integral from 0 to 4. This is e to the 4 minus y minus 1, dy dx. Now integrate with respect to y. This is a 3 here, integral from 0 to 6. Use a u du substitution here, so let u equal to 4 minus y. Du is negative, right? So we integrate here. This gives us negative e to the 4 minus y minus y. Here, the y is evaluated from 0 to 4. This is dx, right? We use a u du substitution, so u is 4 minus y, du is negative dy. So we have that negative sign there from the integration. So evaluate the y at 4. So this is negative e to the 4 minus 4. And minus 4, and then plus, evaluate the y at 0. It's e to the 4 minus 0. It's just e to the 4. And then this is plus 0. So this is 3 times the integral from 0 to 6. This is negative e to the 0 minus 4 plus e to the 4. Dx. So we integrate with respect to x. We get 3 times, here this is negative 1, right? Minus 4 plus e to the 4 times x. X is evaluated from 0 to 6. So we get here 3 times 6 is 18. And this is e to the 4th minus 5. Evaluate x at 0, then we just get 0. Too much. And that's it. Thank you.